Assalamualaikum and good morning. Today we will continue about the Couette flow. So we will focus on the flow between stationary parallel plates. So this is the third combination in Couette flow. So in number one, we have a horizontal plate. One is fixed and one is moved with a certain velocity. And then the second one is we have an inclined plate here without the plate on the top. And the third one is we have two plates like this one, but this plate is not moving, so we let the fluid between these two plates move in gravitational force. Okay, so and then as you know, the fluid will flow downward like this. So and then it will create a velocity distribution. So we have the no slip condition at here, and we could draw the velocity distribution like this one. So and then we know in boundary condition, we could write the boundary condition as show as this one. So means that at y equal to 0 means at this point the velocity is equal to 0, and at y equal to b means at this point the velocity is also equal to 0. So it is okay for you to write this one because this is the real condition at each boundary here. So and then what we need to do is we just use the equation number one. So I hope you could see previous lecture videos, so you could get the equation number one, and then you use the boundary condition that we integrate twice, and then we get these terms. So and then we need to determine what is the value of C1 and what is the value C2 by using the boundary condition. So if we substitute u equal to 0 and y equal to 0, so we could get the C2 is equal to 0. So means that we could neglect the existence of C2 from this point. So mean every time you want to use the general equation, it is okay for you to neglect the value of C2. And then if we apply the second boundary condition, which is the u equal to 0 at y equal to b, so we could calculate the value of C1 as this one. So and then the final equation for the velocity, okay, can be written as this one. This is after you substitute the value of C1. And then we could calculate the maximum velocity, and I think you could guess, you could predict the maximum velocity normally will occur at the center line between the plates. Okay, so and then it is the location, the y is equal to b over 2. So we substitute that, so we could get the value of this one. And then in certain experimental works, we could change the terms here into this one. So this idea is, so we call this term as the piezometric head. So the idea is, we know that this is pressure. So we have pressure is rho, g, and h. So and then rho mu z here. So gamma z here is actually gamma is equal to rho and g. So if we have gamma z, so mean it is also equal to rho, g, and z. So both parameter here, the h here and also the z here is actually represent the height of the water depth. Okay, so and then it will give us the value of pressure. So and then we just simplify this. So this is some kind of if we need to prove our calculation with the experimental work. So we just merge these two terms. So we bring the rho g here outside. So we have a gamma here. And then the h and also the z is actually reflect the height. So we will use the idea of h. Okay. So and then the fluid always flow in the direction of decreasing piezometric pressure or piezometric head. So we give the dHds as negative. So another idea that we could use for this statement is, when water flows, for sure it create pressure drop. So that's why we have DHDS is negative. So another one is maybe from the diagram here. So we assume that if we have graph like this, so if we have graph like this one, so we could get the negative gradient. So that's why the DHDS is showing the negative value. So because it is weird when we get the negative for the Umax, so this is the maybe another purpose for this one. But I think it is good for you to understand that in real life. So if water flows, so it will give us pressure drop. So and then if we calculate the discharge per unit width, so what is discharge? So discharge here, okay, it is equal to flow rate. Okay, so in normally, I think in your undergraduate study, the discharge or the flow rate is symbolized by Q. So and that is the equation is A times V. So this is a very common continuity equation for flow in pipe. So the idea is if we have a pipe here, so and then we have velocity through the pipe here, so we need to multiply the cross-sectional area here, which is perpendicular to the velocity flow with the velocity. So mean the A is here and the velocity is here. Okay, however, the word per unit width here means, okay, let's say we have a square. So a square conduit like this, okay, fulfilled by water. So and then, so if we have a velocity here, okay, we have a velocity comes from it. So we need to calculate the cross-sectional area. So means that the velocity is remain velocity, that V, but the area is the Y here times X. Okay, however, sometimes we calculate in two-dimensional. So mean we assume that the value of X here is equal to 1. It's a unity. So that's why it's right per unit width. So mean that all the value of the flow rate will be divided by the value of width of the channel. So means that we only use A here is x times y. So mean if the x is equal to 1, so we could take only the value of this one, the height of this one. Okay, so that's why in this calculation, so we could calculate the q is integral of u time u dy. So the dy here only show the height of this one. Okay, and then we could get the value of this one. Okay, so and then if we compare with the experimental work, so we could say that the velocity, the average velocity is actually 2 over 3 u max. So this is actually the result from the observation. So and then in experimental work, again, we need to validate our calculation. So it is normally people will do experimental work to prove the Reynolds number. So here it is found that in the textbook, so it will found that Reynolds number less than 1000 is laminar. So but in common application, we could say that the range is 2000. If the Reynolds number is less than 2000, we could say it is fully laminar. So the word fully laminar means 100% is laminar. So mean the molecule, I hope you could study the definition of laminar turbulence. So the important one is each molecule will flow at it on its own path line. So the turbulent means that the molecule has possibility to cross each other path line. It can be it can touch each other, it can collide with each other molecule, and then it in turbulent they will, if they collide with another molecule, they may possibility to bounce back in reverse direction and so on. So because the turbulent is the chaotic flow. Okay. Okay, we have a simple example here. Oil having a specific gravity of 0.8 and a viscosity of 0.02 Newton second per meter square flows downward between two vertical smooth plates placed 10 millimeter apart. If the discharge per meter of width is 0.01 meter square per second, what is the pressure gradient dP for this flow? So first, we need to calculate the Reynolds number because this idea is actually uh, suitable for the lamina only. So the Reynolds number, if we calculate, the equation is rho v d over mu, or in sometimes is rho v l over mu. So and then in this situation, we know the rho, we know the mu, but the problem is might be the v and the d is quite unknown. Okay, so but we have the idea of discharge per meter width. So discharge is the Q is equal to AV. So but if we divide by per meter width, so means the A here is not the area anymore, it will become only the Y. So means we have the Y and V, so it could be replaced the V and B here. So V is the velocity, so same with this one, and the B here actually the depth, the height of uh, the 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 vertical space 10 millimeter apart here. So we substitute the value of this one 0.01. So I show here as Q, and then you will get a 400 there. So it is less than 1000, so we assume it is lamina. So and then we could calculate the value of nu here. So again, in fluid mechanics, please bear in mind that viscosity is the one of the most important parameter. Viscosity is the only parameter that you could get in fluid. So if you deal with solid, so you do not have viscosity. So that's why viscosity is very important in fluid mechanics research. So there are two types of viscosity. So one is dynamic viscosity and another one is the kinematic viscosity. So the dynamic viscosity is mu here, and the kinematic viscosity is nu. So we call it as nu. So I think you already know this one. So and then we need to calculate the pressure gradient. So from the previous calculation, so we have this one. So and then if we substitute the value, so mean we have the 12 mu q here. Okay, and then we could get negative 0.306. So dHds here. So and then from the previous calculation, we could understand that the dHds is actually can be expanded like this one. So and then it is equal to negative 0.306. So we split this term, so it will become dp over so we just have actually the mu, the gamma here is actually gamma is rho and g, and then you know the density and the gravity is not different. So you may write as dp over rho g divided by over ds, and then it will become 1 over ds here, and then it is equal to it's plus dz over ds. Okay, so that's why the rho g here is independent term, so you may have 1 over rho g, so and then you have 1 d rho dp over ds plus dz over ds. So and then because as I said, they are moving, they flow incline downward in negative value, so we give the dz ds as negative 1. So and then if you bring all the calculation here, okay, you will get this one. So this is negative 0.306. We have 1 here, so we bring from the dz ds, and then you multiply with the rho g. Okay, you bring rho g to the right hand side, and then you will get that the dpds is equal to 5,447 Newton per meter square. So in the other word, the pressure is increasing downward at rate of 5.45 kilopascal per meter of length of plate.